In Calculus 2, we learned how to find the center of mass of a closed region in the xy plane with density a function of only one variable. Now this was a huge limitation. Finding the area of this region is rather simple. It's just going to be the integral from a to b of f minus g. But since the density would only change from left to right, when we split this up into small rectangles, we assume that the density going up and down does not change, only left and right. So to find the mass of this shape, it's actually fairly simple. The mass would then just be the integral of the density times the area per m. Now, in order to find the center of mass, we also must calculate the moments. So there are two moments. There's the moment to the y-axis, there's the moment to the x-axis. The moment to the y-axis involves the x distance. So to find that moment, which we generally refer to as m with a subscript of y because it's the moment to the y-axis, although it only involves the x distance, we basically take our mass and we multiply it by x. Now, usually your f and your g functions were fairly friendly. They didn't get too complicated. The tricky part was finding the moment to the x-axis. Because when I take this distance, that's a y distance, and I can't insert a y into an integral where x is the only independent variable. But making the assumption that the density does not change vertically, what we did was we took the midpoint here. The midpoint would be the average of the y values, the average of f and g. So we said the moment to the x-axis then was the average, which would be half the sum, then multiplied by the area parameter. Now when we were finished, we knew that the coordinate of the centroid for x was going to be the moment to the y-axis over the mass. The y-coordinate would be the moment to the x-axis over the mass, and our centroid, or center of mass, is simply x bar, y bar. Now this is how we did it in Calculus 2, but again, some extreme limitations because we could only have density be a function of one variable, and we could only do it in 2 dimensions. Now we want to expand on both of those concepts. Now let's suppose we have a density that is a function of both x and y. Another way of thinking about this is as I move around my enclosed shape, the density at every point is different. So I cannot do this as a single integral. I'll have to do this as a double integral. Now we already know how to find the area of this. In fact, the area would be the double integral over the region of 1 dA. And I would set up my integral as to whichever is easier, integrating dx dy or dy dx. So now to find the mass, I simply insert this into the area integral. So the mass would be the double integral over the region of the density integrated over the area. Very similar to what we did in Calc 2, except now that we have a 2-variable problem, and again, we have 2 different setups we could choose. Now, when we're calculating the moments, it turns out the calculation is probably easier now with multiple variables. Again, the moment to the y-axis, which is the x distance, which we called my, we do the same thing as we did before. It's density times the x-coordinate and then the area integration. But what's nice is that the moment now to the the moment to the x-axis, which is the y distance, I can now insert the y variable because x and y are both independent variables. And this calculation is probably much easier than it was in Calc 1. So like before, x bar, y bar, just like before, is going to be the y moment over the mass, the x moment over the mass, and once again, the y moment being involving the distance to the y-axis. So here's how we do it with 2 independent variables. Now let's look at the 3-dimensional case. Now let's suppose we have some 3-dimensional blob that we can find the volume of, whether we integrate dz, dy, dx, or some other orientation. We're able to find the volume. We know exactly how to do that. It's the triple integral, an integrand of one, integrated with whatever order I choose to make it easier. Now let's suppose the density is defined to be a function of three variables, meaning as I move around the room, the density at every point in 3 dimensions is different. So therefore, I have to integrate a triple integral with an integrand. So in this case, the mass, just like before, would be the triple integral over the volume of the density dV. And again, the boundaries of the region would determine what order you're going to choose. But now we use different notation because I don't have a moment to an axis, I have a moment to a plane. So here's a point in 3 space. The floor is the xy plane. That's a z distance. But if this is the xy plane, excuse me, if this one here is the yz plane, I'm sorry, and if this one here is the xz plane, then I have x, y, and z distances, but not to axes anymore, to actually planes. So I have 3 moments. I have the moment that's the x distance, so that's the moment to the yz plane. The moment that is the y distance, so that's the moment to the xz plane. And the moment that is the z distance, that's the moment to the xy plane. And just like before, I have the same integral, but the additional variable that represents distance. So in this case, it'd be the x distance. So density times x dV. In this case, it would be the y distance. So density y dV. And in the last case, it'd be the z distance. So density z dV. And just like before, our center of mass would involve x bar, y bar, z bar, where x bar is the moment to the yz over mass, y bar is the moment to the xz over mass, and z bar is the moment to the xy over mass. And again, our centroid would then be x bar, y bar, z bar. The final thing you want to write is the actual position, but this is how you find centroid. Now, there are no difficult problems if the functions you're dealing with are simple, which they usually will be in this case. Now, I've put a very long, extensive example on Canvas. It's one problem, but it's quite long, and we calculate each of these individually.